Tesla's world's first solid-state battery just did what Toyota, QuantumScape, and Samsung couldn't. And by the end of this video, you'll understand exactly why every other automaker just got left a decade behind. This isn't about specs or hype, it's about walking away with the clarity to explain why this specific breakthrough means the line between the old automotive world and the new one just moved, and there's no going back. The solid-state promise that never came. For over a decade, solid-state batteries have been the industry's most broken promise. Every year, another company announces they're just 5 years away from commercialization. Toyota said 2025, QuantumScape said 2024, Samsung promised breakthrough after breakthrough. But here's what nobody wants to admit. They've all been solving the wrong problem. While legacy automakers threw billions at making solid-state batteries work in theory, Tesla was quietly asking a different question. Not, can we make it work in a lab, but can we make it work at scale, profitably, tomorrow? That question just got answered. What makes solid-state different? To understand why this matters, you need to know what makes solid-state batteries fundamentally superior. Traditional lithium-ion batteries use a liquid electrolyte to move ions between electrodes. It's effective, but it comes with 3 fatal flaws. First, liquid electrolytes are flammable, which is why EV fires make headlines. Second, they degrade over time, which is why your phone battery dies faster after 2 years. Third, they're bulky, which limits how much energy you can pack into a given space. Solid-state batteries replace that liquid with a solid ceramic or polymer electrolyte. The result? No fire risk, minimal degradation, and energy density that makes current batteries look primitive. Here's the number that matters. Tesla's new solid-state cells reportedly achieve 400 watt-hours per kilogram. For context, the best lithium-ion batteries today max out around 260. That's not an improvement, that's a category shift. The 3 barriers nobody could break. But if solid-state is so superior, why hasn't anyone done it yet? Because 3 engineering nightmares stood in the way. Barrier 1, dendrite formation. When you charge a solid-state battery, lithium metal can grow tiny spikes called dendrites that pierce the solid electrolyte, causing short circuits and catastrophic failure. Every solid-state prototype in existence has failed because of this. Barrier 2, interface resistance. Solid materials don't naturally bond well at the atomic level. The connection between the solid electrolyte and the electrodes creates resistance, which means slower charging and power loss. Toyota's been stuck on this problem for 7 years. Barrier 3, manufacturing cost. Even if you solve the first 2 problems in a lab, producing solid-state cells at scale requires entirely new production methods. QuantumScape spent over $2 billion and still can't manufacture cells profitably. Tesla just solved all 3, and they did it without anyone noticing. Quick question. How many years have you been hearing about solid-state batteries being almost here? Drop a number in the comments. I'm betting most of you are thinking 5 or more. Let's see if I'm right. Tesla's secret weapon, the Maxwell acquisition. The key to understanding Tesla's breakthrough goes back to a $235 million acquisition nobody paid attention to. In 2019, Tesla quietly bought a company called Maxwell Technologies. Most analysts dismissed it as a minor deal for some capacitor patents. They missed what mattered. Maxwell had developed something called dry electrode coating technology. Instead of using toxic solvents to apply electrode materials, Maxwell's process uses raw powder and pressure. It's faster, cheaper, and eliminates a major production bottleneck. But here's what Tesla saw that nobody else did. Dry coating is the missing link for solid-state production. Because solid electrolytes can't handle wet processing, every other manufacturer has been trying to retrofit century-old battery production methods that fundamentally don't work. Tesla didn't retrofit, they rebuilt from scratch. The silicon anode breakthrough. The second piece of Tesla's puzzle came from solving a problem everyone thought was impossible. Lithium-ion batteries use graphite anodes because they're stable, but graphite has terrible energy density. Silicon can store 10 times more lithium than graphite, which means 10 times more energy. The problem? Silicon expands by 300% when it absorbs lithium, cracking the battery structure and destroying it within cycles.
For decades, researchers tried coating silicon particles, mixing them with graphite, or creating complex nanoscale architectures. Nothing worked at scale. Tesla's approach was radically different. They developed a silicon nanowire matrix that flexes as the material expands. Think of it like a sponge instead of a brick. When lithium flows in, the structure accommodates the expansion without cracking. Combined with their solid electrolyte, this silicone anode delivers unprecedented energy density while maintaining structural integrity over thousands of cycles. The result? Lab tests show Tesla cells retaining 94% capacity after 5,000 cycles. That's not 200,000 miles, that's over 2 million miles before you see meaningful degradation. If you're realizing right now that Tesla's been playing chess while everyone else played checkers, make sure you're subscribed, because what's coming next makes this look like just the warm-up. Hit that button so you don't miss it. The cost equation that changes everything. But performance means nothing if you can't manufacture it profitably, and this is where Tesla's advantage becomes impossible to catch. Current lithium-ion battery production costs hover around $100 per kilowatt-hour. Tesla's 4680 cells brought that down to about $90. Industry analysts predicted solid-state batteries would cost $250 to $300 per kilowatt-hour for the first decade of production. Tesla's claiming they can hit $65 per kilowatt-hour at volume. How? 3 reasons. First, their dry electrode process eliminates expensive solvent recovery systems and cuts production space by 30%. Second, solid electrolytes use cheaper materials than the complex
lithium salts in liquid electrolytes. Third, higher energy density means you need fewer cells for the same range, which reduces assembly costs. Do the math on a 75 kilowatt-hour battery pack. At $65 per kilowatt-hour, Tesla's total battery cost drops to $4,875. That's less than what competitors pay for their current lithium-ion packs before they even start assembling the vehicle. This isn't just a better battery, it's an unbeatable economic moat. What this means for range and charging. Now let's talk about what this actually does for the cars you'll be driving. With 400 watt-hours per kilogram energy density, a Tesla Model 3 could achieve over 700 miles of real-world range with a battery pack that weighs less than current packs, delivering 350 miles. But range is only half the story. Solid-state batteries can handle much higher charge rates without degradation. Current superchargers pump out 250 kilowatts, adding about 200 miles in 15 minutes. Tesla's solid-state architecture can theoretically handle 500 kilowatt charging or higher. What does that mean in practice? A full charge from 10% to 80% in under 8 minutes. That's faster than filling up a gas tank, and you're doing it while grabbing coffee. But here's the part nobody's talking about: temperature performance. Lithium-ion batteries lose 40% of their range in cold weather because the liquid electrolyte becomes sluggish. Solid electrolytes don't have this problem. Tesla cells reportedly maintain 90% of their rated capacity at minus 20 degrees Celsius. For anyone who's ever watched their EV range plummet in winter, you just got your car back. Be honest, would 700 miles of range finally kill your range anxiety? Comment range if yes, or charging if faster charging matters more to you. I'm curious which one people care about more. The safety revolution. There's another advantage that might matter even more than range, and it's the one that's kept EVs out of parking garages and cargo ships. Lithium-ion batteries contain flammable liquid electrolyte. When they fail, they don't just catch fire, they experience thermal runaway, where one cell ignites the next in a chain reaction that's nearly impossible to stop. Fire departments can't extinguish lithium-ion fires. They can only contain them and let them burn out. This isn't theoretical. In 2022, a cargo ship carrying 4,000 vehicles, including EVs, caught fire and burned for weeks. Insurance companies now charge premiums for EV transport. Some buildings ban EV parking in underground garages. Solid-state batteries eliminate this risk entirely. With no flammable liquid, thermal runaway becomes physically impossible. You could puncture Tesla's solid-state cell with a nail and it wouldn't catch fire. You could overheat it, overcharge it, or crush it, and the worst that happens is the cell stops working.
For the insurance industry, this is the moment EVs become insurable at parity with gas cars. For consumers, it's the moment range anxiety gets replaced by the last psychological barrier falling away. Why competitors can't follow. So, if Tesla's breakthrough is real, why can't Toyota, GM, or Volkswagen just copy it? Because they're trapped by their own infrastructure. Legacy automakers have spent $50 billion building lithium-ion battery factories. Those factories use wet coating processes, liquid electrolyte filling systems, and assembly lines designed around current cell formats. Retooling for solid-state production would mean scrapping billions in capital investment and retraining entire workforces. Tesla built their battery production from scratch with solid-state in mind. Their gigafactories were designed with modular production cells that can be reconfigured as technology evolves. When you don't have legacy infrastructure, you don't have legacy constraints. But the deeper problem is intellectual property. Tesla's solid-state breakthrough relies on 3 patent families: dry electrode coating from Maxwell, silicon anode architecture from their internal research, and proprietary solid electrolyte formulations developed in partnership with academic researchers. Those patents create a moat that competitors can't cross without either licensing from Tesla or spending a decade developing workarounds. And here's the kicker: Tesla's not interested in licensing. Elon Musk open-sourced Tesla's EV patents in 2014, but battery technology, that's staying proprietary. The competition isn't 5 years behind, they're starting from zero.
If you've been following legacy automakers thinking they'll catch up to Tesla eventually, this is your wake-up call. Subscribe now because the gap just went from years to decades, and I'll be breaking down exactly what that means for every major car company next week. The grid storage wildcard. But the biggest disruption from Tesla's solid-state breakthrough might not be cars at all. Grid-scale energy storage is the bottleneck preventing renewable energy from replacing fossil fuels. Solar and wind are now the cheapest energy sources on the planet, but they only generate power when the sun shines and the wind blows. To make renewables viable, you need batteries that can store energy for days, charge and discharge thousands of times, and cost less per kilowatt hour than natural gas peaker plants. Current lithium-ion batteries almost make the economics work. Tesla's Megapack installations are already profitable in many markets, but the batteries degrade too quickly, requiring replacement every 10 to 15 years, which eats into long-term returns. Solid-state batteries with 5,000 cycle lifespans change the equation completely. A grid storage installation that lasts 30 years instead of 10 becomes 3 times more profitable. And because solid-state cells can discharge at higher rates without degradation, they can handle peak demand spikes that currently require natural gas plants. If Tesla can produce solid-state cells at $65 per kilowatt hour, grid storage becomes cheaper than any fossil fuel alternative. Not in 2030, not in 2040, next year. The entire energy infrastructure just became obsolete. So when will you actually see these batteries in a Tesla you can buy? According to sources familiar with production timelines, Tesla is currently pilot producing solid-state cells at their Cato Road facility in Fremont. Volume production at Gigafactory Texas is expected to begin in late 2025, with initial cells going into the Cybertruck and Semi. Here's what that means in practice. The first Teslas with solid-state batteries will likely be limited production models, possibly a special edition Roadster or high-end Model S Plaid variant, launching in 2026. Mass-market vehicles like the Model 3 and Model Y will transition to solid-state by 2027 to 2028 as production scales. But don't expect Tesla to announce this with a big event. They'll do what they always do: quietly start delivering vehicles with dramatically better specs and let customers figure it out. No press releases, no hype cycle, just cars that drive 700 miles on a charge and cost the same as current models. That's how you know this is real. Tesla doesn't announce breakthroughs, they ship them. Here's the real question. If you're shopping for a Tesla right now, do you wait until 2026 or buy today? Comment wait or buy and let's see where everyone stands. This is actually a tough call. What this means for you. If you're deciding whether to buy an EV now or wait, here's what you need to know. Current Tesla models with lithium-ion batteries are still exceptional vehicles. They'll last 300,000 miles, charge on the existing supercharger network, and hold their value better than any EV on the market. If you need a car now, don't wait. But if you can delay a purchase until 2026 or 2027, you'll be buying into a completely different technology generation. The jump from lithium-ion to solid state is comparable to the jump from flip phones to smartphones. It's not iterative, it's categorical. For current Tesla owners, the question is whether solid-state batteries will be retrofit compatible with existing vehicles. Tesla's historically offered battery upgrades for older Model S vehicles, swapping in newer cell chemistry for improved range. If they continue that policy, you might be able to upgrade your current Tesla to solid state for a fraction of the cost of a new vehicle. But the bigger implication is for anyone who's been on the fence about EVs. Range anxiety, charging time, cold weather performance, fire risk, every objection that's kept people in gas cars just got answered. The transition from internal combustion to electric isn't coming, it just arrived. The domino effect. What happens when one company solves a problem everyone thought was impossible? The automotive industry is about to find out. When Tesla launched the Model S in 2012, legacy automakers dismissed it as a niche product for tech enthusiasts. By 2015, they were scrambling to develop their own EVs. By 2020, every major manufacturer had announced plans to go all-electric. Tesla forced the industry to change by proving EVs could be desirable, profitable, and manufacturable at scale. Solid-state batteries will trigger the same domino effect, but faster. Within 12 months of Tesla delivering solid-state vehicles, every competitor will announce accelerated timelines and massive R&D investments. Within 24 months, the first partnerships and acquisitions will emerge as legacy automakers try to buy their way into the technology. But they'll be too late. The companies that win the solid-state transition will be the ones that started building the infrastructure years ago. Tesla, BYD in China, which has its own solid-state program, maybe one or two startups that pivoted early enough. Everyone else becomes a commodity manufacturer, competing on price for a product they don't control. The hierarchy of the automotive industry just reset. This is just the beginning of the biggest industry shakeup in 100 years. If you want to understand who wins and who disappears in the next 5 years, subscribe now. The next video breaks down exactly which car companies are already dead and just don't know it yet. The questions nobody's asking. But there's a darker side to this breakthrough that's worth understanding. Solid-state batteries require lithium, just like lithium-ion. And while they use less per kilowatt-hour, the total demand for lithium is about to explode. If Tesla scales production to 20 million vehicles per year by 2030, all using solid-state cells, lithium demand will triple current global production. Chile, Argentina, and Australia control most of the world's lithium reserves. China controls most of the refining capacity. Geopolitical tensions around battery materials are about to intensify in ways that make oil politics look simple. There's also the labor question. Tesla's gigafactories are heavily automated, requiring fewer workers per vehicle than traditional auto plants. As the industry shifts to solid-state production, manufacturing jobs will concentrate in a handful of facilities, leaving traditional auto manufacturing regions behind. These aren't reasons to reject the technology, but they are realities we'll need to navigate. The line just moved. So here's what just happened. For a decade, solid-state batteries were vaporware, a technology that worked in labs but failed in factories, a promise that was always 5 years away. Tesla didn't announce they were working on it. They didn't hype a prototype. They didn't promise a timeline. They just solved the 3 problems nobody else could solve, built the manufacturing infrastructure to produce it at scale, and created an economic moat that competitors can't cross. In 2026, you'll be able to buy a Tesla that drives 700 miles on a charge, recharges in 8 minutes, lasts 1 million miles, costs the same as current models, and has 0 fire risk. That's not a better EV. That's the moment internal combustion became legacy technology. The line between the old automotive industry and the new one just moved, and if you're still deciding which side of that line to be on, you just ran out of time to wait. Last question. What's the one feature from this solid-state breakthrough that changes everything for you personally? Comment range, charging, safety, or cost. I want to see what matters most to real people, not just tech reviewers. If this breakdown finally gave you clarity on why solid-state actually matters, hit that subscribe button right now.
because next week I'm revealing which legacy automaker is secretly closest to matching Tesla, and the answer is going to shock you. And drop the word yes in the comments if you're now convinced that buying a gas car in 2025 is like buying a flip phone in 2010. Let's see how many of you just became believers.